Let's see. If we look at the test, oh, wrong page. We go to the take-home test. Well, let me go through this. Okay, so if you go to the site, you go to classes, you go to the Google Drive, you go to our class, you'll see all the take-home tests in there. And they should show up like this, unless there's something about your system browser. This one is a fairly simple one. I'll go ahead and talk about this one now. Okay. So looking at this problem, you need to think about it like this. You're essentially an accountant, and you're counting for all the energies, the 1/2 m v1 squared plus 1 plus mgh plus 1/2 k delta squared. In the first, if there is no energy lost, and the energy would be lost through a term like this. Oops, that looks pretty funny. It would be lost through a term like this. Then you're simply accounting for all the kinetics energy and the potential energy. Just so happens that there is no spring. So all you're doing is identifying the initial velocity, the initial kinetic energy. If you look back at this problem, the whole thing is smooth. Everything is smooth. If you'll notice, you'll notice it says the surface is smooth. All of this surface is smooth everywhere. So all you need to do is account for the block weighs 10. That's all you need to account for. There's your spring, there's your G. I don't know what that arrow is showing up there is. Anyway, all you're accounting for is that. And so all you have to do is do an accounting of the energies. There is no loss of energy here. So that's all you're doing is an accounting for the energies. You have the thing starts from rest. It's at a particular location, so you have an energy that you start with. If you set your datum such that that location is 0, all you have is kinetic energy. So we'll call it good with that one. What I'll do is make use of my giant lassoing tool and hit the big global delete. So there was that. Let's take a look at the second problem. Second problem is a problem that looks kind of confusing. I'm going to relate it to a problem that you can see in the text, and I'll just go ahead and make a halfway decent attempt to draw a similar problem to one there. So I'm going to pause it and draw. All right, here's the problem. And in essence here, we see something very similar across the board to our problem. First thing we need to do is, okay, this thing is set. So this one is 60 pounds. This one's 40. Now, if you didn't know what direction this thing moved, you need to determine it. Okay, how would you determine it? Well, you know you got to generate a free body diagram anyway. So let's proceed to do that. We'll start with the one on the right, or they'll call this one B and that one A. Okay, so I know I have a tension that runs up this direction. I have a normal force that runs in this direction. I have a weight which comes straight down of 40 pounds. Um, 30 degrees there. So I could call this tension. This is the normal. Now, technically, what the biggest thing is, if this block goes upwards, the friction will go this direction. But if the block goes down, friction goes in that direction. So the key is which one does it go? We don't know yet. Let's say we're not given that information. What we'll do is we'll draw this other block. Okay, we'll draw it. And on it, I essentially have two tensions here. I have the weight coming down of 60. And it's 60 degrees, not related to the other 60 at all. And I do have a normal here. Guess I'll need to delineate between those two. If it's a static type problem now, somebody has to hold one of the blocks. So you can just pick one of them to work off of the other. It really doesn't matter, so I'm going to pick this one. I'm going to pick this one right here. In picking this one, what I'm going to do is I'm going to use this one to figure out what tension is, and then move it over to this one and determine was I having to hold this one, push it that way, or push it this way to keep it in static equilibrium. Let's progress through here and I'll show you what I mean. So we need to figure out what, let me see if I can rewrite this weight here. If I redrew the weight so that it started here, came down, I'm interested in finding out that value as well as this value. That being the 60 degrees and this being the 60 pounds, then this value right here is 60 times the sine of 60. And if it was in static equilibrium, now that's the key, if it's in static equilibrium, this value would be mm-mm. 51.96. Now, if it was in static equilibrium, then this value should be equal to that, giving you the tension. That being the case, you get 25.98. So you would get a tension equal to 25.98, the static tension. Now, we're going to have a dynamics problem in a minute, so that's not going to be what happens here. If that's the case, now I need to redraw a few things over here. Now let's go ahead and get rid of some of this mess here to keep things from being too confusing. And I'm going to do the same thing over here. Okay, I have a weight that goes this way, this, and this one. And the, oh, shoot, let's see if I can bring that back. Okay. And the angle here, why am I getting this? Okay. The angle here, right here, is 30 degrees. So therefore, this value becomes 40 pounds times the sine of 30 degrees, or here, should become just 20. But if this thing is 25.98, then this force overruns this one. Therefore, since this is larger, the motion occurs this way. Moves up the plane. This one moves down the plane. Now that we established that, the first thing you recognize is this is not going to be the value for the dynamic tension. And we can prove that in a minute. But for right now, we're not going to. We're just going to say, okay, we know now the direction it moved. Now let's say if one of these blocks, say, moved 2 foot, or let's just say, what would the velocity be if this one moved 5 feet? Or maybe, yeah, that's good enough. So if this one moved 5 feet, then what were the velocities at that point? Now what I'm going to do is, I think I'm going to go back and address this later. So I will basically highlight this to come back to it. But I'm going to keep it highlighted and keep it there, but I'm going to erase all evidence of it. And I'm going to say now that I know this block is moving in this direction. I know the frictional force will be like this. And if that one's moving up and this one's moving down, this frictional force will be like that. And the question is what's the frictional force going to be? Well, I need to know what NA is. Okay. So on this one, since this was the sine, this one will be 60 cosine of 60, or 30 pounds. Let's say mu is equal to 1. Okay, then this 30 pounds will turn into 3 pounds right there. This one, on the other hand, in B will be 40 cosine of 30, or around 34.64 pounds, which means that this frictional force will be 3.464. Now I've got all my forces here, so let's take a look and let's go through this. Okay, I'll change colors. Okay, so what I have is MAGHA1 plus MBGHB1. If it's released from rest and there's no spring, the only thing I have now is, I'll do an F. F, force due to friction on A and B. On A, dotted with the distance A moved, plus force due to friction on block B, dotted with the distance B moved, equals to now MAGHA2 plus MBGHB2. Now I do have velocities. MAVA squared, 2 squared, plus 1/2 MBVB2 squared. Now I can start looking at these things. Okay, here really doesn't matter if block A moved down 5 and it was a triangle that looked like this, where this is 60, then this is the height we moved to. So if I pick state, here's the states, state 1 and state 2, this is for A. If I did the B triangle, okay, here's 30. However, let's do our little SAs and SB. Length of our rope is equal to the delta plus 2SA plus SB dotted a couple times, and what you get is 2SA dot plus SB dot. If, say, A moved 5 foot in so many seconds, then B moved the distance that B moved over the same time, whatever that time is. That has to equal 0. So apparently, if this is 10, so apparently the distance that B moved will be 10 up the plane. So there you go. This distance is 10, and this is the height that B moves, where this is the height that A moved. So let me highlight both of these. This is the triangle and the distance for A, and this is the one for B. This means I can set my datum wherever I want. How did this end up being this way over here? Well, this is state 1, and this is the point that is state 2. So here I'm going to take my datum this way. Over here I'm going to take my datum this way. So this means that, okay, notice this is B. So if you look at it, this is associated with B here as well as B here. That being the case, I'm saying that this value right here becomes 0, and this value right here becomes 10 times sine of 30. Now, if I do something similar over here to A, I'll take this being HA, this one being state 1. Well, then that means, the way I have it, this one is 0, and this one is 5 times sine of 60. Now, in order to reduce confusion here, go ahead and take these markings off here. Okay, so what I have is the mass of A, which was 60 divided by 32.2 times 32.2, which is G, which actually I don't like that, so I'm just going to put it in there as a straight up 60 times 5 sine of 60. This term gives you 0. This term, what does it give you? Well, first of all, let's take a look at something. The motion of A was down. The friction is up. Since these are in opposite direction, the dot products become negative. So as a result, all friction components become negative like that. And your biggest concern now is what these are. Minus force of friction at A. I think we found force of friction at A was 3 pounds. The distance we moved was 5. Okay, let's look at that. Okay, here was our 3 pounds. It came from this times the mu that showed up here, and the distance we moved was 5. Again, let me do that again. Okay, with a different color. Okay, we found the normal times friction gave us 3. We're moving, and this was the distance we moved was 5. Okay, similar concept over here. They both show up with a negative. The frictional force was 3.464. And what distance did we move? We moved this block a whole 10 here. In other words, here's our 10 we moved. Here's our friction force. Here was our NB, which gave us our 3.4. And we got that. So we moved a whole 10 there. So this term is right here, and this term is right there. Equal to, now I have nothing here, but I have MBG. MB times G was a 40-pound block times 10 sine of 30 plus, okay, here I've got this MA, which is now, I can't get away without 32.2. VA squared plus 1/2 of 40 over 32.2 times VB squared. Now up here, we have a relationship between those two. Here, what we can do is use our little lasso tool, grab the thing, head down the page. There. Put our equation down there, which actually should have been highlighted by that, but I guess it wasn't. Okay. So if you look at this, you will notice that it no longer matters the sign of this, because whatever they end up being squared in these terms. So it means 2 times velocity A plus velocity of B equal to 0. Doesn't matter whether they're positive or negative. Whatever the value of the velocity here is, this it ends up being twice the one that's here. So I got two choices. Find velocity A, find velocity B. Since I don't want to deal with halves, I'm going to take this one and put into here. Which by doing that, I think I'm going to take this value in this one and put on one side of the equation. So let me see if I can work this out, and hopefully it turns out to be okay. If not, we'll come up against something interesting here. $60 times 5 times sine d of 60 minus 3 times 5 minus 3.464 times 10 minus 40 times 10 times sine d of 30. It looks to me like I got a 10, oops, 10.167. 10.167 goes over here. Then I get 2 times VA squared plus 1/2 40 over 32.2 times 4 VA squared, which gives you VA squared equaling to, or VA squared, let's see, okay, VA equal to square root of 10.167 divided by all this stuff. Let's see if I can figure that out. What is the stuff first? Here, I'll do this on this one. Keep that as a variable. I'll say B is equal to 0.5 times 60 divided by 32.2 plus 0.5 times 40 times 4 divided by 32.2. And I have a mistake right there. Okay, so square root of A divided by B, if I solve that correctly, I got 1 point something. 1.725. 1.725 is equal to velocity of A. I have an interesting question though. Now what's the question? What? Okay, first, do you think there would be a point in which I could end up with a zero velocity for A or B or whatever? Okay. For example, I ran this thing 5 down the plane. Okay. So in other words, I decided that this was going to run 5 foot down the plane. What if I run it 50? Let's see how everything relates here. How does it relate? 1, here's my 5. Here's my 5. Now, here's a 10, which is related to 5, and so is that one. Now, I'm proposing a question. How far does it have to go down the plane until it's scrubbed off the energy? Is it possible that it could do that? Or does it just simply stop? Does it stop or does it not stop? So let's say there ended up being a point in which there was a possibility of no further kinetic energy. In other words, all the potential got converted into friction energy. Let's take a look. 60 times the distance it moved down the plane, 30 times 60, minus 3 times the distance it moved down the plane, minus 3.464 times 2 times the distance it moved down the plane, out of the pulley, out of the, the rope equation, equal to 40 times 2 times the distance it moved down the plane times sine of 30. Now, one of the things I want to look at is I want to observe how the velocity behaves as associated with this d. Okay, so I'm going to do something interesting. I'm going to combine this term together and this term together, or look back and see what it was combined together. And I think, if I'm not mistaken, it was this term and this term. Okay, let's double check here. Let's see if I can scrunch this up. Move it down. Hit the draw in there. Okay. 1/2 of 60, 32.2, and 1/2 40, and 4 and 32.2. So I got my 40, my 4, 32.2 and a half. Okay, I got my 4, 40, 32.2 and a half. So I think the B is my major number. So here's what I'm saying, 3.41. So I should put a 3.41 here. Okay, let's remember that number. Okay, 3.416 plus 3.416 times velocity of A squared. So now I'm going to try to put this in and figure out what it is. Some constant number times d equals to 3.416 times the velocity of A squared. What's the constant? Well, let's try to find what C1 is. I might be able to get that by going back here to A Or I might be able to just produce it. Let's see, C1 is equal to 60 times sine degrees of 60 minus 3 minus 3.464 times 2, and then minus 40 times 2 times sine degrees of 30 ends up being 2.0335. 2.0335 distance it moved is 3.416 BA squared. So if I wanted to look at this as a function of that, I'd be able to produce that. Let's take a look. Okay, so I have C. Now what was A? Was A my, no, A was not, what was B? B was my value. So this right here, this is B in my Scilab, and this was C1 in the Scilab. So you'll see what I'm doing in a minute. So look at D equal to 0 from 0.01 to, say, 20. And then I want to do my velocity equals to square root of C1 divided by B times D. Then I want to do a plot of D versus V. Okay, so what you get here, let's see if I can put a label on it. D is out the axis here. The velocity is here. So in other words, if I'm seeing this correct, this was my X. So this is the distance it moved. And this is the velocity. So you can see when you initially let it loose, it's at rest. It increases fairly rapidly, but then it sort of ends up like this. But this is a quadratic, and I'm pretty much done with this problem. I sort of overdid it there, so I apologize about that.